Good morning. Let us start. I think this was the last slide we discussed last time. Any questions about anything we've discussed? Okay. If no questions, let us go on. And what I already said last time, in fact, but let me here reiterate the whole idea of traceability is comparability. The reason why people want to make their measurement results traceable to the same point of origin is that they want all the results of the same type of measurements be comparable wherever in the world that they can be made. And comparability is possible if results are in the same units. True, in many cases, units can be converted. For example, joules and calories, or kilojoules and kilocalories, these can easily be converted by 4.184 joules per kilocalorie, etc. So that energy is expressed in joules and kilocalories, although not directly comparable, but can be very easily made comparable just by unit conversion. But it is very important that the units mean the same thing. Yeah? And secondly, results are traceable to the same reference value that provides the same size of unit. So this is exactly what I have in mind. Yeah? You may know that, for example, mile, the length unit mile, if you look up in some, let's say, more sophisticated source, you find many miles. For example, the usual mile is 1.6 something kilometers. But there's a nautical mile, which is a completely different mile. And then there are even more miles. So this has to be avoided at any. So this is what makes results comparable. These two. Any questions here? Okay. And what should that reference and what should those references be? Right now, wherever possible, the ultimate reference should be the SI unit. So that if we go back now to this scheme, this high-level intercomparison, so-called key comparison, establishes the unit. So that whichever etalons that we have here are traceable to this, the results of this key comparison can be called traceable to the SI. And obviously, kilogram is not the only thing. Yeah, there's all those other, like ampere and meter and so on. All of those are right now defined via different fundamental constants, so that you need some devices that sort of involve those constants and like reorganize them into those measurement units, like the Kibble balance in the case of mass. I will give you a little bit of information about that in the coming slides. So traceability to the SI unit. And of course, we are not living in an ideal world, so not always can you make results traceable to the SI. Like octane value of gasoline is not traceable to the SI unit. I don't know how much you know, but the octane value is determined by some kind of, let's say, test engine. So there's a specifically built engine in which you can change the parameters. And so you put the fuel in and you run that engine, and then you determine what the octane number is. It cannot really be in any meaningful way converted into the SI unit. And there are other such technological measurements of that sort. Now, most of what I explained was about physical measurements, and now we try to go closer to chemistry. And here I'm now going to eventually present to you pretty much along the lines of the EURACHEM traceability guide, this traceability of chemical measurements. Almost always, with few exceptions, are amount of substance measurements. And there's the unit of amount of substance, which is called the mole. We will come to that. The substance we usually call analyte. And in this context, at the moment, I'm only speaking about targeted analysis. So non-targeted analysis, or analysis that actually does not have an analyte, where you simply examine some changes in spectra or something, which can be very useful in technology, etc. Out of each student, those of you who go to Lyon, you might end up doing exactly that kind of work. So that is right now completely outside of the discussion. So we discuss situations where we have analyte or analytes, and we really want to get the analyte by concentration or mass, whichever way we like to express it. And now, as I said, the amount of substance unit is the mole, which you all know very well. But if you express your results in milligrams per liter or milligrams per kilogram or micrograms per kilogram or whatever, like mass per volume or mass per mass, it still is amount of substance. Even though formally, if you look at milligrams per liter, it's formally mass measurement and volume measurement. Yeah, and like formally, one could ask the question, hey, wait a minute, where is the amount of substance? But the important thing here is that these milligrams are not just some milligrams. These are very well-defined milligrams of that analyte. So this is what is very important. So in chemical measurement, its mass is not just mass, it's mass of the analyte. And this is what makes it amount of substance measurement. And if we have well-defined analyte, then always we can recalculate milligram per kilogram to millimole per kilogram, or milligram per liter to millimole per liter. So it's very easy to recalculate using atomic masses or molecular masses. And those atomic or molecular masses will be very important things in the coming slides. I will explain that. Now, this specific requirement of a specific analyte is what makes chemical measurement very, very different from physics. So the analyte must be a defined entity, and essentially we could say that every different substance is a different measurement, so that in fact the mole is just a generic term. We have so many moles as many we have potential analytes. So let's just it may be easy, not so easy to understand, but let me try to explain. So suppose you are measuring luminosity, light intensity, light coming from some kind of source. And all the photons that come, you collect and then you measure. And that there might also be, okay, I want to measure luminosity only in certain wavelength range, etc. So there might be some like physical constraints. That is typical physical measurements. All photons that come are good photons. You collect all of them and you measure. If now you do some spectrochemical analysis, like atomic emission spectra. This is also, in a sense, luminosity measurement. There's some radiation, you measure the intensity, yeah? And then you, by a calibration graph, you recalculate. But now it is not so that every photon is a photon that you're saying. In fact, you're only interested in photons that come from your analyte. And in physics, you might say, hey, wait a minute, yeah, but we are interested in photons that are, let's say, in the range of 347 to 349 nanometers. In chemistry, we could also say, yeah, we are interested only in those. But on top of that, we are still, it's not the question which range, it's the question who emits those photons. And if in that range, some atom that is not your analyte also is emitting, then those photons are bad photons. They are interference. You should get rid of. So this is what is different. The same thing about mass measurement, the same thing about current measurement. So a lot of analytical chemistry like boils down eventually to current measurement, all those detectors and also in all electrochemical measurements. Current or potential, and in gravimetry, it's mass, etc. But again, not every mass is a mass in chemistry. You are only interested in mass of your analyte. This is what makes chemistry so much more difficult than physics. What makes chemical traceability like stranger thing than in physics. So what I just tried to explain is captured in this sentence. So you measure some radiation intensity. You are interested only in photons that are emitted by those atoms that are your analyte in this particular analysis. And this is different from all other assignments. Let me stop here for a moment and ask you, please raise your hand who thinks that understood this difference. Okay. Falong, Ekta, did you understand? Ekta, okay, good, very good. Everybody understands. And now let's look at mole for a moment. This slide, this was my slide in the past, before 2019, before redefinition of the kilogram and mole. I'm still keeping it for historical reasons, but it's not true anymore. And then the mole was defined via 12 grams of carbon isotope 12. So mole was defined via kilogram. So if you look here, there's an arrow going from kilogram to mole. Kilogram itself was defined by this piece of metal. Yeah, this is now history. So you can, essentially, you can forget this slide. Yeah, it's just for historic reasons. Now we are living in this world. And the mole is now defined via the Avogadro number. 1 mole of substance is the amount of substance that contains this number of entities, entity being atom, molecule, some molecular, supramolecular assembly, etc. So many, it can be several things, but most frequently it's atom, ion, or molecule. And kilogram now you see is completely disconnected from the mole. Yeah, there's no arrow. This Kibble balance uses meter and second and Planck constant. So this is how kilogram is now defined. Shame on me, I'm not able to explain you how Kibble balance works. You can look it up yourself, but perhaps not so important for the purposes of this course. So that now the mole is very nicely defined, exactly as it should be, number of entities. And this value of Avogadro number now has uncertainty 0. Does not have uncertainty. It's definitional number. In the past, Avogadro number had uncertainty, defined by a kilogram. Now it does not, which is a nice thing. Again, the uncertainty was so microscopic that for any real life measurement, that was essentially uneven. So that the change was fundamentally very big. Yeah, it was done in 2019. But in practical terms, whatever we do in our labs, not really. Does not really enter our lab work, actually. But it's useful to know these basics. And now the mole has like two applications or two uses. One is measurement unit. Yeah, you can express your measurement results as moles or moles per kilogram, etc. But this is not so important. Usually, labs don't express measurement results in moles per liter. Also, if you look at legislation documents or some industrial standards, it's mostly not in moles. Milligram per kilogram, milligram per liter, percent by mass, ppm, all those, which are typically mass to mass or mass to volume kinds of. In gas metrology or gas measurement, it's also oftentimes volume to volume. Yeah, usually. So more important is the conceptual value of the mole. Mole as concept is related to the number of certain particles in certain object, and particles being molecules, ions, atoms, most commonly. The next two lines very important. It's the atomic masses and consequently molecular masses, which you get as sums of atomic masses, that enable first of all, recalculating mass to mole, mole to mass, and also recalculating the or relate the amounts of different substances to each other. So that, again, if you do some very, very simple things, such as the titration of hydrochloric acid solution with sodium hydroxide, then the mass of hydrochloric acid that reacts with a certain mass of sodium hydroxide is defined by the ratio of their molecular masses. Yeah, so they react in mole ratio 1 to 1. Yeah, and so the molecular mass ratio defines how much of one is needed to react. And we as chemists, for all kinds of standard solutions, titrants, etc., we most of the time use mass measurement to obtain amount of substance needed for calibration. Most of the calibration solutions are prepared in such a way that you take the pure substance, you weigh, and make a solution. And by weighing, you essentially will know the amount of substance. We usually don't express in moles, but it still will be traceable to the moles. No? So if you have any mass of any real substance, you immediately know how many moles of that substance. So that, very basically, we could say in chemistry, we establish traceability by weighing. If you want to, it's simplified. It's simplistic, simplified, not the full story. I will come to that. But if you want to say just one sentence, very simple sentence, how do we establish traceability in chemistry? Traceability of amount of substance. Then the answer would be, we establish it by weighing pure substances and calculating amount of substance on the basis of atomic and molecular mass. This is the most fundamental thing that you can say about traceability. But as I will come to in a moment, this is not enough. Please again raise your hand who thinks that understood. People on the internet, yeah, okay, Carlo. Carlo, hi there, did you understand? Good, everybody raised. This is how weighing becomes so immensely important. And I think sometime in the very beginning of this course, when we discussed uncertainty sources, we also discussed uncertainty of weighing. And I said, yeah, modern balance is very good. Yeah, they enable high accuracy, but I also stressed that you should not take weighing lightly because so much depends on it. And this here explains why weighing is so prominent and so respected activity in chemistry, that the traceability like goes back to weighing. Okay. So, and now essentially saying the same thing like over again. In our case, the stated reference on chemical measurements is atomic masses of elements and weighing data. The atomic mass is what is obtained according to the definition of the mole. It essentially means that you need to take into account what exactly are the atoms, also what are the possible isotopic compositions, etc. Yeah, so you know that there are many elements which are not monoisotopic, so the atomic masses are not really integer numbers, but they have some commas and so on. And weighing data and atomic masses are the link between mole and kilogram. Mole and kilogram are linked by atomic. So, any questions? Let me just once again ask, please raise your hand who thinks that understands this. Elvin, either. Okay. Now, if we would be living in an ideal world, we could go home now, because traceability sorted out. And what follows now from this point on is because we are living in a non-ideal world, where you have interferences, where you have extraction recovery below 100%, all those nasty things, yeah, that creep. There are some people who say that all of those things are not traceability things at all, that they are related to measurement uncertainty, something else, so the traceability sort of stops here. But the EURACHEM guide still puts a lot of emphasis on all those other things also, yeah? And we will also look at it. And now here comes a scheme of formal traceability of amount of substance, which is a small like extension of what I just explained. And let me already now say that these two things here in red are those that are not covered by the formal traceability. So these are not covered by the formal traceability. And this is why we need this like more sophisticated thing. So how do you do? First of all, you make standard solutions by weighing the pure analyte. This can be either your calibration standard solution or your titrant. You know, of course, that, like, for example, sodium hydroxide as a titrant, you cannot really create accurate concentration by weighing sodium. It's hygroscopic and it's not pure and so on. But then you do so that you weigh some standard acid, like maybe like succinic acid or oxalic acid, etc. You make standard solution of acid, and then you standardize your titrant that way. So it becomes more sophisticated, but the essence remains the same. So you take pure analyte, most cases, and you end up with standard solutions. And you make instrumental measurements with those standard solutions, and those instrumental measurements with standard solutions give you what? Calibration graph. Yes, you make calibration. Again, it's simple. There might be internal standard and all kinds of different things, but in simplified terms, this is how it is. Okay, now you have your calibration ready. Now you extract your analyte from the sample. You weigh the sample and you do some volumetry. Volumetry meaning that, okay, you weigh, then you dissolve, maybe you dilute, maybe you do all other kinds of things. And then at some point you get sample solution. With that sample solution, you again do instrumental measurement. And now you have your calibration graph, and this instrumental measurement gives you the analyte signal or the analyte peak area or the analyte voltage or whatever it is that you are measuring. And now you compare these two and get analyte content in the sample. And comparing these two essentially go like this. This is essentially the comparison. You put your signal. These are here your calibration graph parameters, and you get your constant. And this is all very simplified. The CX might still need to be converted to the sample. They're dividing by some mass measurement, but that's not so important. Solved. Traceability finished. But this beautiful scheme operates in an ideal world where all your measurements are infinitely selective, there's no interferences, and extraction recover is always 100.00000%, so you don't lose anything. Of course, there's no contamination and no volatilization and no sample carryover, all those things up. And EURACHEM has put forward a scheme, which of course is based on this essentially, which also addresses those additional problems or those potential additional problems. So, EURACHEM SciTAC approach, they put forward a stepwise procedure. And when you have all those steps or stages completed, you can claim that your result is traceable to the stated references. Perhaps it's fair to say what that means. In this case, I'll come to that later on also, but chemical measurements typically will be traceable to mole, the SI unit mole. Also the SI unit kilogram, because this is the amount of sample, how you measure, and then oftentimes, or mostly also to the SI unit of meter, because all volumetric measurements have to be, or volumetric measurement results have to be traceable to the meter. So very often it's like traceable to the 3 SI units simultaneously, and this is nothing very special or nothing very exceptional. If you think for a moment, for example, pressure. Pressure is force divided by area. Yeah. So pressure is always pressure measurement, if we want to make them traceable to the SI, are traceable to the kilogram, are traceable to the meter, and actually also to the second, because kilogram times meter per second squared gives us the force, so that many measurements are simultaneously traceable to several SI units. So that chemical measurement results mostly are traceable to mole, kilogram, and and how do you achieve that kilogram and meter? I'll explain that also. So here is the scheme laid out. It's 5 steps. Finding the measurand, always the first one. Choosing suitable method, and this is important. It's the method itself and it's the model equation that also needs to be suitable. So the method is like composed of two different things. Then you need to validate them. So the EURACHEM traceability guidance explicitly requires that you validate your method. And obvious. Validation takes care of selectivity. Validation takes care of extraction recovery. Either you correct or you put it into uncertainty. Validation, in the context of this thing, it ensures, first of all, that the model adequately describes the measurement. For example, if you use linear calibration function, that it still is really is linear, and that you can use it with reasonable accuracy. And of course, that measurement conditions are adequate, so that selectivity is taken care of, recovery is okay, and so on. So validation, in a way, does all these takes care of these problematic aspects. Incomplete extraction, sample carryover, incomplete selectivity, or all those. And then you establish separately traceability of all input quantities by some reference materials and or calibration, and I'll explain that in a minute. And finally, no traceability chain is complete without uncertainty. Measurement uncertainty of the result is also finally. So this is how it is. Now we go step by step. We look at one example, which is nitrate content in dried plant material. WNO3 minus expressed in milligrams per gram. So this was step number 1. Step number 2 is now the method. Yeah, first of all, the measurement procedure, sample treatment. People weigh the sample, extract the nitrate from it. Extraction can be just with water. Nitrates are very well soluble. Preparing solution, yeah, and diluting it if necessary. And then instrumental analysis, getting some signal or peak area, ANO3. And then secondly, calibration. For the sake of simplicity, I have here adopted simple one-point calibration. In practice, I would always recommend calibration graph, not one-point calibration. But here it is simply easier to do the explanation. So that you prepare a standard solution from, let's say, potassium nitrate, and also measure the signal, yeah, in the chromatograph, also some kind of. And of course, calculation of the result. Okay. How does this look model-wise? Oh. In order to get concentration of nitrate from the plant material in the solution, in this solution, we divide the signal of the analyte obtained from the sample with the signal obtained from the standard solution and multiply with the concentration of the standard solution. This is the typical one-point calibration where you do, like, if you want to express it as a calibration graph, then one point is 0, 0, and the other one is the calibration concentration and the calibration signal. So simple proportionality. Again, I would not recommend to use it in practice, but here in the explanation, it is suitable. This here is the comparison. So in one of the previous slides, I said, oh, yes, we have the signal from the sample and the signal from the calibrant, and now we compare. So this is here, this comparing. Then to get the amount in milligrams of the nitrite in the sample, we multiply with the volume and also take into account dilution. Dilution factor, FDI, is simply the ratio of one volume to another volume. Dilution factor does not have any units. It's simply a ratio of volume. So that suppose there's a lot of nitrate and you need to dilute 10 times. Yeah, so that like pipette 10 milliliters into 100 milliliter volumetric flask and fill it. Now you have the amount, and now if you want to express it relative to the mass of the sample, so that you would get milligrams per gram, then you divide by the mass. Finally, if there was recovery significantly different from one, then you may want to do also recovery correction. Here I have explicitly put recovery correction in, but as we've looked at it in this course, you can also do so that you do not correct for recovery, but instead you take in additional uncertainty term, which reflects your recovery possibly being different from you. Okay. And here are all these quantities explained together with units. So let me stop for a moment, look at this and ask any questions. No question. Okay. Next step, validation. So what are those main things that validation needs to establish? There are more, but I've only here indicated those that are right now really related to this discussion here. Yeah? So for example, I'm not bringing out LOD here, which might be also important. So first of all, very importantly, is the signal really from the analyte? So is this ANO3 really the analyte signal, or does it partially come from something else? Any overlap with any other peaks? And can we be sure there are no interfering peaks underneath our analyte? So we should do also blank studies and then The next thing, model equation. Okay. Does the method determine all the nitrate in the sample or only part of it? So the recovery here is meant to take into account this. If only we find that only part of it is extracted successfully, then we should either correct for recovery or increase the uncertainty. So that incomplete extraction in our case has been accounted. Okay. Next thing, measurement conditions. I said previously that you have to check linearity, and if you do 1 point calibration, then it's actually very serious. When you're doing 1 point calibration, which again I don't really recommend. If you do 1 point calibration, you have to be absolutely sure that between these two, 0, 0, and your point, that it really is linear. So you have to separately carry out linearity study, and also you only can do 1 point calibration if your intercept is indistinguishable from 0. If you have positive, constant positive intercept or negative, some cases might be positive, then you cannot. Then you simply cannot use 1 point calibration. So 1 point calibration only works if intercept is indistinguishable. So these are all things that, of course, in any of your normal chemical analysis, you should take care anyhow. But the way EURACHEM explains it is that this is part of establishing traceability. So this is what EURACHEM does in a way differently from some other explanations and some other sources. They say that you cannot claim traceability if you haven't validated the method, which I very much agree. It's a very good. Good. Calibration. Reference standards with demonstrated traceability. That's interesting. How, suppose now you do this kind of analysis, you have you make calibration graph. I mentioned potassium nitrate. How, maybe let me ask you, suppose now you are making calibration solution of potassium nitrate. How do you ensure traceability of the concentration of that solution? What do you have to have? Yes, Christian? Yeah. Where is this microphone? It's over there. Okay, it's near enough. Yeah, if you speak from there, it's near enough.
But first of all, I would like to greet everyone that today we're celebrating the 150th World Metrology Day. So it's a perfect timing that we're discussing this, right? And going back. I was reserving the question for a later, but I think it's the perfect time. So I would like to say that calibration solution or calibration standard are not created equally. So, I mean, in that matter, a potassium nitrate that is sort of like the one we usually commercially purchased isn't the same as the potassium nitrate that was developed with highly method characterized by some metrology institute perhaps, and that has this kind of documentation in the case of certificate of analysis. And of course, when you want to ensure traceability, you would want that type of material or standard than the one we are less confident with. So that's perhaps one the way we prepare or choose what substance we are going to use.
Okay, so one thing is the substance. Yeah, I'll come to the substance, but it's not the only thing. What else must we do if we want that concentration to be traceable to the SI? As I said, chemical measurement results are traceable to several units. we weigh on a balance which calibrate. Yes, okay, good. And now, yeah, we put some water, yeah, and what is important there? Yeah, okay, yes, water purity indeed also, that it would not contain nitrate. I would say this is pretty okay. Yeah? If you take water from those water purification machines, then it's okay, but... Sorry?
Volumetric glass? Like...
Yes, volumetric glass. So in principle, your balance and your volumetric flask have to be calibrated so that your mass measurement and volume measurement are also traceable. Right? Calibration of the balance is done, again, in different ways, but let's say the most correct way is that some calibration person or calibration company from time to time comes to your lab with etalon weights and checks it and issues calibration certificate. Daily check should be done then with this, let's say, daily check weight. And as for volumetric flasks, the modern volumetric flasks, when they come from the factory, can already be considered factory calibrated. Although, if you want lower uncertainty, you should recalibrate them yourself. Higher uncertainty than you maybe want. I would say in most practical work, the uncertainty which they have is good enough. I think I explained you the uncertainty of volumetric work when we spoke about the uncertainty sources. But you can reduce the uncertainty by calibrating yourself. Now the standard substance here, it actually is in a way like the most difficult, yeah, and Christian is perfectly right that not all calibration solutions are equal. With potassium nitrate, you can buy like certified compound, yeah, for high price, yeah, and very high purity. With the large majority of possible analytes, you just don't have a certified chemical. So that usually it also is considered sufficient if the chemical simply is of sufficient purity, but you have to have some information about purity so that you can assign to it uncertainty due to purity, which I also explained sometime in the first part of this course. Because in many cases, sadly, we are forced to use compounds for which the manufacturer simply says that, okay, the purity is 98% plus, yeah, which means that it's anywhere between 98 and 100% the substance content. But then if you have to use that, you have to take into account this purity, uncertainty of. Regarding the metrology, yeah, shame on me. I should. I know this, but somehow did not think of it, and I did not know that it's 150. Okay, and indeed, since many metrology people consider traceability like the fundament of metrology, then it's a very significant, yeah, that it's exactly today that we are discussing. Okay, so yeah. We do this, yeah, and then we have our calibration solution, yeah, and if we prepare the solution from potassium nitrate, then of course getting nitrate concentration is not difficult at all, yeah. If you have the molecular mass of potassium nitrate and the molecular mass of nitrate ion, yeah, so you can express it whichever way. This is one of those cases for which I said also that via atomic and molecular masses, compound amounts or amounts of substance are related to each other. I brought this sodium hydroxide, hydrochloric acid example, but here the relation is just the same. Whenever we have concentration expressed as potassium nitrate concentration, it's very easy to recalculate the nitrate ion concentration and then vice versa. Yeah, and now we can now look at how do we establish traceability for the input quantity. So, importantly, it is not required that you establish traceability individually for all these quantities. So, these two can just be handled as a ratio of signal intensities measured on the same instrument, so that you can regard them as quantity without units. Yeah, so that like this ratio certainly does not have units. And if the standard solution, was made the way we just explained, then we can say that the calibration sort of establishes traceability for all these parts. We can consider that these three input quantities now are covered. Then we have volumes. Volumes can be made traceable by either manufacturer certificate, or you can calibrate your volumetric wear yourself. Mass measurement is, of course, possible by calibrating the balance. And I've put here the dotted lines. Dotted lines mean that if you calibrate your volumetric wear yourself in the lab, then you will most likely do weighing, and then taking into account density of water. And then, of course, temperature comes in, so that it is, then you also will be using gravimetry for calibrating your volumetry. And finally, for determining recovery, if possible, you can use matrix certified reference material. And as we discussed about matrix certified reference materials, if they are correctly prepared, from prominent producers, then their reference values are traceable to the SI. Or, well, in the case of chemistry, are traceable to the SI. And technological measurements. So, any questions? Okay. If not, then the last thing is evaluating the uncertainty of the result. If you have traceability established for all the input quantities, then in principle, you also have the uncertainties of all the inputs. So that in principle, this would be like a very good case for the ISO-GAM. But in practice, you may still have big issues with uncertainty of recovery. As we saw in this course, uncertainty of recovery is not really easy thing to establish. There are some assumptions and things. And it also is not required to use the ISO-GAM uncertainty evaluation approach. It is perfectly valid to also evaluate your result uncertainty with the NOR test. You can still declare that it is traceable if you have done all of this and then evaluated the uncertainty using the NOR test approach. It's very okay. Nothing wrong with it. And if you did all that, then you can say traceability is established. And if you now look at what I explained here, then you may remember we discussed the certificate of the certified reference material, and I was slightly like critical. Traceability very superficial, only one sentence or something. Here you now see it's not so easy. Actually, there's a pretty much of quite a bit of activities that you need to carry out. Let me wait. Any questions? And then I have one more slide. Okay, let me say few more words about calibration. So there are different types of calibration. So some of them we already discussed here in this course, but let me try to make some like big picture, if you wish. So the most common, by far, the most common way of doing calibration is calibration curve or calibration line with standard solution. It can be either with or without internal standard. Typically, if you do some like simple, let's say, spectrophotometry, etc., then usually people don't use any internal standards. In spectrophotometry, it also is very difficult to do actually technically. In chromatography, it's much more common, but also if it's like main components, usually not so important. But in trace analysis, it's like a correlation. The lower you go with concentration, the more important internal standard. For example, I'm not really an expert on ICP-MS, but I've told that in ultra-trace ICP-MS analysis, you should like almost never do without the internal standard. You should always use internal standard there. I would say the same with LC-MS at trace level also. And if your detector is mass spectrometer, which oftentimes it is, if you do trace analysis, then isotope labeled internal standards really are very similar to your analysis. And the other thing that also may be different is whether the calibration standard solutions are made in solvent or whether they are matrix matched calibration. To quite some extent, internal standard helps avoiding the need for matrix match, but not fully. So that, for example, if your matrix is something which is quite common, then matrix matched calibration graph can be quite good. What I mean by common, it means that you have to be able to obtain blank matrix which really is very similar to your matrix. Good example here is, for example, blood plasma, which is, although biomedical analysts say that blood plasmas also differ from person to person very much, but still blood plasma is still like more or less the same thing. Its composition cannot be very different because then the person just is not alive anymore. If blood plasma has a very different composition. So in the case of blood plasma, yes, you can do the sample preparation, which oftentimes is like precipitating proteins and then a few more things, and then you get this solution which you would get after sample preparation from your sample. And now you put measured quantities of the analyte inside, and your whole calibration line will then be in blood. If now, in contrast, we look at soil, and I've been explaining here numerous times how different soils are, so that one soil might not at all be suitable as a matrix matched calibration matrix for another type of soil. Moreover, even more in more similar, seemingly more similar cases does not really necessarily work well. In the past, now it's actually already more than 10 years ago, in the past, one of our group members carried out a wide-ranging study of LCMS matrix effects on apples. And what she discovered was that matrix effects differed between apple varieties. So not only is apple and orange different things, but apple and apple are different things in terms of matrix match calibration. So she determined some pesticides, and she discovered that matrix effects in different apples were distinctly different. Meaning, just by matrix matched calibration, if we speak about apples, not really possible at all to take the matrix effect into account. So either you need to hugely increase uncertainty to account for it, or you need to use internal standard. Yeah, okay, so yeah, again, it's very dependent what you are analyzing, and yeah, in many cases it does work. Yeah, like with blood plasma, I've understood it quite commonly used to do matrix match calibration. But in some other analysis, not so. Okay, so this was calibration curve. The second big thing is standard deviation. Standard deviation, of course, ensures matrix match, because you are adding the amounts of analyte to the same solution that you obtained from sample preparation. So matrix match problem is solved with standard deviation. And standard deviation can also be done with and without the internal standard. But of course, standard deviation is very much more work intensive, because you need numerous measurements for every single sample, because essentially every single sample will have its own, like a small calibration. It's not a calibration, but it looks like calibration. So it's a lot of work. And also, if there is some interference that simply is present and not recognized by you, then matrix, if it's constant interference, then matrix matched calibration does not help. So standard deviation does not help. So standard deviation helps for those effects that deviate the slope of the calibration graph. For example, if there's something in the matrix that suppresses ionization proportionally in all samples, then matrix match, then standard deviation works. But if there's simply some additional intensity in constant way coming into all the solution, then standard deviation does not have any benefits at all. So that it removes some issue, but does not remove some others. Nevertheless, it's sometimes. I would again say that not really clear whether you will use it in routine analysis when you need to analyze tens or hundreds of samples. But for your like master thesis or your PhD thesis, in difficult situations, I would certainly consider, if suppose there are some extremely important samples, maybe there are not so many, but it's so important, you need to get as close to the true value as possible, then I would certainly recommend run them with calibration and run them with standard deviation. Compare the results. If they are matching, well, that's an additional argument in favor that, okay, yeah, you probably didn't do too well, but maybe you get completely different results, then of course, yeah, there's a reason to be. Okay. Last thing, which is not really fully calibration, but also should be handled here, is isotope. I have So I actually, in the past, I even had separate part of this course about it, but I decided to leave it out. The course is already so big, so in order not to make it too big, it's not much used in routine laboratories. And also in research, it is used in certain specific cases, but not in some others. But it is used extensively in metrology institutes, top of the top labs, and for producing certified reference. Isotope dilution works. Let me just explain in very brief terms. Works in such a way that you take your sample and you extract part of analyte out of it, yeah? And for some, let's say, for a given mass of sample, you get some intensities or something. And now a second aliquot of the sample, you add your analyte with a different isotopic composition. This is especially used in ICP-MS for making trace element reference materials. Then you need isotopically enriched elements, yeah, which oftentimes are available, although might be very expensive. You add a well-known quantity with different isotopic composition. You again run the sample preparation, extract it out, and again you get some signals. Yeah, you get the signals of the different isotopes, like you did in the first case. And now, from some mathematics, you can recalculate how much analyte you had in your sample initially. Oh, yeah. You also do so that you add with normal composition also. Yeah. This is what you also can do. And the beauty of this approach is that mathematically it follows into such a logic that your extraction recovery becomes unimportant. You don't need to it's of course good if it's high, yeah, but extraction recovery can nicely be like 60 or 70%, and you don't need to worry. So with isotope dilution, it is important to just extract part of the analyte so that the signals are visible, can be accurately measured, but does not need to be the whole. And the whole game is about ratios of signals in mass spectrum. I did not mention this in the beginning, but it's all isotope dilution is mass spectrometry. Yeah, so it all relies on mass spectrometry. You cannot do that with infrared spectrometry or UV visible or something. And it's usually, of course, for trace analysis. The main issue with isotope dilution is that, again, you need to be able to disperse your analyte, this isotopically enriched analyte in the sample, exactly the same way as it is original. So if any of you is interested in that, then you should get guidance from some really experts, which I am not. But let it simply be said that if for example, if you buy some CRM and somebody writes there that yes, this and this and this participant used isotope dilution mass spectrometry, then you know that it's probably well done. This isotope dilution is not used by simple labs. It's only used by top laboratories, very high level. So, questions?
Sorry, it was not clear for me. Like in the standard edition, we have like our sample, like our blank matrix. That's why you were talking like that matrix match was assured with that, right?
In standard edition, you don't need blank matrix. It's just your sample. It's just your sample.
Okay.
You divide your sample into a number of aliquots. To the first aliquot, you don't add anything. The second one, you add a little bit of the analyte, then a little bit more, still more, and still more. And then you get a graph of 5 points. Okay,
Yeah, I was confusing. With
think quite-
matrix, you use the blank, and the standard edition, you use the
yeah, in a
Yeah, yeah.
matrix matched calibration, you need blank.
yeah.
But in standard edition, what you do is this thing. Try to.
Because it's extrapolative, no? Like
It is, yes.
Yeah.
Yeah, true. So now let's take your. I'm not. All right, now, yeah. So suppose now that these are now your data points.
Mhm.
Yeah, sorry, stupid me. The first data point has to be exactly on this axis.
Mhm.
This is the one where you did not add anything at all, yeah? These are all your data points. And now you put a line through them. I think it does not allow me to send the line outside of the box. Okay, but that's not really a big. In any case, this line is extrapolated here, and this length here will be the amount of analyte. Yeah, let me also put added concentration. It's not the concentration, but the added concentration, and up here is this. And yes, you don't need the blank.
Yeah. And here you were saying that if we have like ionization suppression or enhancement, like it will be completely unnoticed. But in matrix match is not the case, no? Like because we carry out matrix match in order like to figure out if there are some matrix effects. But here, those matrix effects will become unnoticed is if the effect is the same in all the cases, right?
By the word unnoticed, what exactly do you mean?
Because you were saying that if we have, for example, this ionization suppression, and we are using this kind of calibration, we will not figure out if matrix effects are happening or like are taking place.
We are not figuring out, and we don't have to. So if the matrix effect is proportional, so that you always lose, let's say, 30% of your signal, signal becomes 30% lower, then standard edition is a beautiful method. Because yes, as you correctly say, we do not notice, but we don't have to notice, because everything will still be fine. But if it's not proportional, but constant, some effect, here usually it's not suppression, but some enhancement. So suppose there's some interferent in the sample, which also generates the signal. But there's a constant amount of it, so it increases the signal in all these solutions. Then you simply get the line. So unfortunate. So if you have some constant interferent, then this is what you get. See, you get higher line, you get overestimated concentration, and you don't know that you had this. But if it's just ionization suppression, which is proportional, then your true calibration graph without ionization suppression would look like this. Okay, yeah. I can always. So your true calibration graph would be like this, and you will have this. So the slope differs, but the point of intersection with x-axis remains the same. So that, yes, matrix effect goes unnoticed, but does not make your concentration wrong. If it's constant signal, then also it goes unnoticed, but it makes your concentration wrong. So this is why I asked what you mean by unnoticed.
Thank you.
It's unnoticed in both cases. Elvin says, so standard edition does not address selectivity only. Yes, Elvin, in a way you are right. It does not help us against interference of type 1. But it can help us against interference of type 2. If you remember, this matrix effect is caused by interference of type 2. Interference, which is not the analyte, does not generate the signal for the, but it disturbs the method in some way, which in this case is the matrix. So yeah, Elvin, your point is very good, yeah? It addresses selectivity only in terms of interference part 2 and not necessarily all of these, but it does not at all help against interference of type 2. Okay, any other question? If not, then I have here the last discussion question. Yeah. So in principle, you should, of course, if possible, calibrate your instrument every day you use it. Some instruments it is occasionally done, not as frequently. It's done more rarely, maybe once a week or twice a week, not every day. What are the considerations how you can do? Which ones absolutely need to be calibrated every day? Which ones might not be calibrated maybe every day, although would be recommended? This is now not really a metrology question, but like instrumental question.
UV-Vis was not required to like create a calibration graph like regularly.
UV-Vis is a good example of an instrument which, yes, perhaps you don't need a calibration graph every day, but what makes it so good? For example, can you do the same with something like flame atomic absorption spectrometry or ICP-MS machine or this liquid chromatography mass spectrometry with electrospray source? Not really, UV visible. And let me add one more thing, that X-ray fluorescence machines, for example, are sometimes bought with calibrations of these handheld machines. Calibration already inside. It's already inside from the factory. And the other good example is near-infrared spectrometers, which are used, for example, in food industry. They use calibrations made of many hundreds of samples, occasionally few thousands of samples, and those calibrations are bought together with the instrument. There's no way you would be able to do within a single day that kind of calibration. That just absolutely doesn't work. Making such calibrations is a big, big, big work. They are multivariate statistical analysis based, PLS, etc. So again, some of you who end up in Lyon for the second year, you might encounter that kind of work there. So, but what determines which instruments can be like that, which instruments cannot?
Parameters, for example, UV-Vis like doesn't have a lot of like changeable parameters.
Very well said. Yes, In some instruments, you need to change parameters from day to day, yeah, and then of course the previous calibration doesn't work. But even that is maybe not the most important thing. One more thing. It's a very simple answer, actually. Maybe again, one of those questions which is too simple to just cannot imagine that I can ask so simple thing. Stability of instrument in time. And now, whenever you have something like gases, flames, then there's no way you can have a stable instrument which would be exactly of the same stability. Moreover, mass spectrometer ion sources typically are very unstable, very irreproducible things. Like, for example, electrospray source is notorious for today behaving like this, tomorrow like this. Now the electrospray has this thing, and now it's not in good mood. So all kinds of things happen. So electrospray MS, absolutely you have to do calibration. But now those instruments that are purely optical, like UV visible spectrophotometer, yeah, there's a source, all this optical things, fairly stable, yeah. And also source energy can decrease in time. But in UV visible spectrophotometer, if you measure absorbance, then you know that the absorbance is ratio, logarithm of ratio of intensity. So even if source intensity changes, nothing happens. Yeah, the absorbances will still be very, very similar. The same about these XRF machines, they can be very stable, near-infrared machines. But even with those instruments, if you don't do calibration every day, there's at least one thing you must do. And this is some kind of test sample, just even one sample that you run every day to check that it has the same peak and the same reading or the same signal, yeah, that you had yesterday. So that is absolutely necessary for all of those. Like, for example, these XRF machines that are bought together with calibrations. Yeah, you don't do calibration every day, but you check your calibration every day. There's some block of metal or piece of ceramic or whatever, depending on what you are measuring. That block or ceramic thing you measure every day. If that will be within limits, then good. If not, you have to take some measures. Also, pH meters occasionally can be quite stable, but then again, I would never trust a pH meter without checking with at least one calibration. Don't need to rerun calibration every day, perhaps, if you know that it has been so stable, but checking is important. And also, before deciding that, yes, this instrument does not need to be calibrated every day, before deciding that, you have to work with the instrument for some time, making many calibration graphs and being sure, yes, indeed, they all look essentially the same. Maybe I don't need to do it every day. So you should not just trust it. Yeah, somebody in the lecture told me that the UV visible spectrometer is very stable, so I'm not going to calibrate it. Absolutely not. First, you do it every day, and only then, when you see that it's really stable, you can start doing it also. All right, this essentially ends our lecture, and this also ends the lectures of this course, because this is the last slide. Now let's talk a little bit about the future. So on 1st of June, you will have the test. You wanted to have it from 4 to 8, yeah, in the afternoon, yeah, okay. This will be programmed. Once you start, you will have 1 hour. 1 hour is far enough. Yeah? And on that test, there's also a little bit of calculation. So you need either Pocket Calculator or Excel. So make sure that you have either of them. It's not a difficult calculation, but you need to know the formula. Yeah. And the test is without material, so you're not allowed to check them. So that you can look at our material, what formulas we have. It's not a difficult formula, but I'm not going to say which one it is. So it is one. There's a little bit of calculation, but most of it is still clicking and finding the right answers. And I think in test one, correct me if I'm wrong, I think we said that there are 3 correct answers or 2 correct answers, etc. In test 2, it's not said. There are several correct answers, or maybe several, but we are not saying how many. Oh, be prepared, yeah? There are not many questions, but read very carefully. In some cases, differences between variants are just one word. Those of you who take the seminar, you experience something similar in the seminar test. Yeah, sometimes very similar sentences. Here's the small difference. And this small difference might make one variant completely wrong and the other one right. Yeah? Again, it's not, I would not say it's so difficult test, but it's not trivial. And also, this test cannot be failed. If you get 0, it's also fine. Yeah? Only you lose points from your final exam. Is also the reason why this test cannot be retaken. You do it only once. And then exam. At least one person has wanted to do the exam before the test. That is possible, if you wish. Simply, I'm not going to be able to tell you exactly the exam result on the exam day if the test will still come in the future. But once the test result is in, the grade will be calculated. Are there any other of you who would like to do exams still in May? Would help me to adjust. Nobody. So you all plan to do in June, I understand. Okay. Then I will know that I'm not. I'm going to propose some bunches of exam times, and I will put them in Moodle so that you can check. You can choose times. If still somebody discovers that no, I still need to do the exam already in May, shout at me, write me, and we will organize. So it is possible to do it. Before the first exam time, we certainly, I mean, before the first period when a number of you will be doing exam, we will do a tutorial hour. Right now, doing tutorial hour, I think, is too early. It's better if you already have been learning for the exam, because then you have more questions. For that one student who already wished to do exam earlier, he can contact me separately. I can do some small tutorial, like on a personal basis, if need. And I will announce tutorial hour and tutorial hour times when we have already some exam times fixed. So it will probably be somewhere in the first half of June, or let's say in the beginning of June. Let's see how it goes. Also, whoever has special wishes for exam time, you can also email me. You don't need to wait until I propose any exam times. You may be like, you may need to travel somewhere. There's the internship thing, and all those things might be an influence. Yeah. Of course, since exam is via Big Blue Button, you don't need to be in Tartu. You can be in another place doing your internship. You can be even in your homeland or in your second year university. You will need good internet connection, but you should not be overly stressed, because suppose we agree on exam time, you come and then the internet connection is so bad that we cannot do. This does not mean you get the bad grade. We will simply reschedule the exam. So you will certainly not suffer. I mean, you suffer like emotionally. I wanted to do today. I could not. But your grade will not suffer from bad internet connection. You don't need to be very much stressed about that. We will find a way. We've had internet problems, and we've always found a way. No problem. Now, one of you asked about scheduling exam time into July. I still haven't replied to the email, but perhaps I use the opportunity to reply here. I don't really want to schedule exam times in July. It is in principle possible to do in July. But I would leave July for like unforeseen circumstances, resits, and also some, let's say, really difficult situation. For some reason in June was not possible. So let us try to get all your exams done in June. And if something really happens, or maybe, okay, many things can happen. You can fall ill. I can fall ill, yeah, and be like out of work for some time. Then, of course, we will consider July. But July is already like, let's say, how is it? So the formal end of semester is somewhere at the end of June. Yeah. So we should try to do it in June. Again, it is possible in July. It has been done in the past, but I would like to keep that to a minimum in order not to make that a rule. So, what else? I think I've said pretty much all. It's 11:46, yeah? Oh, almost perfect timing, yeah? So, if any questions? Apparently not. Yeah.
How the exam calculations?
Okay, yeah. I think I said that, but okay, it's not difficult to repeat. Yes, we have oral exam and calculation. It works as follows. You will have your exam time. You will come to Big Blue Button. I will ask you to say a number from like 1 to 6. I have several variants of exam, and every number corresponds to some bunch of questions. Once you say your number, it's a random number. You don't know what questions will be. I will copy into this chat, yeah, I will copy your exam questions. Then you have something like, let's say, 15 to 20 minutes for preparing, and make maybe schemes and then write down some points for you to make it easier for you to read. And then we discuss, I ask things and so on. Please also note that oral exam has the specific property that whatever are your initial questions, I can ask about anything. Yeah. So let's say, okay, suppose it's like the question is something about making this is about making calibration graph and okay, the potassium nitrate, etc. But from here I can start asking something about certified reference materials and then maybe about production of certified. So this talk can wander wherever. I may want to ask about anything. We start with, of course, those questions, and mostly we stick to them. But be prepared to answer any question. Once that is done, you have answered or not answered if you don't know, yeah? Then we close, and then I will give you your practical exercise. You get your practical exercise, and then you have several hours for doing it. We stop the session. Yeah? Usually I do it so that if the exam is like in the midday or in the afternoon, then I say that you have time to do your calculations until the next morning, so that I would want to have it in the next morning in the Moodle. You have to upload to the Moodle. So you have a lot of time. I mean, you have hours. Calculations, all I'm saying, do not rush, read carefully, do carefully. I don't want you to be pressed. So by next morning, you upload them. And next morning, I will check your calculation and I will contact you. And we usually do so that we, again, briefly meet in Big Blue Button where I explain what you did right, what you did wrong. And then I give you the score and your final grade. So if the exam is after test number 2, then the next day after the exam answer, you will know your grade. So you don't need to wait until I check it. During calculations, you are allowed to use all materials. We've said you are allowed to watch the videos if you wish. You are allowed to use any files. You are allowed to use your friends' files, but you are not allowed to contact your friend. If you want anything from your friends, you have to ask them before the exam, not during. So once you have your practical task and you start doing it, you are not allowed to communicate with anybody, but you can use any resources on the internet, any books, any files that you have in your PC, etc. And also be prepared that I may want to ask something about your calculation. Sometimes I get the, sometimes I suspect that you may not have understood all what you did. Just put numbers somewhere into some like file that we did here in class. And if I get the suspicion, maybe the person didn't really understand why this cell has this formula, then I may start asking, okay, this cell, this formula, explain why you multiply by this. Explain why you subtract this one. Why not this cell? Why that cell? I don't do that very often, but I do some. If I then discover that, aha, person has just mechanically put in numbers, doesn't really understand what he or she did, sadly, there will be not so good grades for the practical exercise. Very useful to understand. And also, you don't even need to wait until the first tutorial class. Whenever you start learning for the exam, there's the, what is it called now? Discussion. No, discussion slides, yes, but there's the thing in Moodle which is called questions and answers forum. Yeah, there's forum, questions, answers. You can write all your questions there. It's very useful because all people will see, and others might also have the same question. I will then reply. And okay. Any questions? Okay, and unless it wasn't clear, tomorrow no class, Friday no class, next week no class. These regular lectures are. So then I wish you all the success, yeah, and we close now. Yeah. If anything, communicate with me. Thank you.